Ay, Dios mío. Goodness gracious. Okay, so I was muted. So here I go again. Ugh. There goes our 30 minutes. All right. So basically, what I just got done saying, right? It's hopefully y'all could still watch me right? So, like a radical is basically that little symbol that looks like a house, and then a rational is a fraction. So, for a square root function, right, we have the square root, and your domain starts at 0 as well as your range, because we cannot take square roots of negative numbers. That's not possible, right? So if I give you the number -4, there's no number you can multiply by itself to give you a -4, right? -2 times -2 is +4, which we know that does not equal the -4 we want. And if I do 2 times 2, then that's obviously a +4 again. -2 times 2 is -4, but that is not a perfect square because one number is negative, the other one's positive. Okay, then we have cube root of a function where the domain and range can be from -infinity to +infinity. Um, and then hopefully this example right here that I wrote down here, um, that domain and range goes both ways because we can take the cube root of a negative number. And then I gave you that little example right there, okay, as to why the domain and range is different for both of these. Now, transformations. It is the same rules that we've been doing since the beginning of the year. Looking at y'all's exam that y'all just took, y'all are really good at telling me translations. For the most part, you can tell me if it's translating left, right, up, or down. Where we seem to have a little bit of trouble is identifying if it's a stretch or compression. Not necessarily if it's vertical or horizontal. It's really more, do you know if it's a stretch or compressing? The other thing y'all forgot about a lot is this negative symbol right there. Y'all forgot about the negative, like a good chunk of you forgot about the negative in one of those questions. So we just need to make sure that we're looking for all things that are different in the function and we're identifying all of it. Okay, so right here, I gave y'all a little helpful hint. So I have radicals don't really have parentheses, right? We'd have, oh, hold on. Right here on our radical symbol, there should be like a little n. Oh, why isn't it working? Oh, there it goes. Right, because we don't know what root we're taking. But anyway, so if you have something inside the radical, then it has to be horizontal. But if you have something outside the radical, then it is vertical. Very similar to what we've been doing before, right? That concept still applies. Is it inside or is it outside? If it's inside, then, horizontal. If it's outside, vertical. Okay, so the example that I did with you first, that I did for you all the way, was describing the transformation of this cube root. So we have the parent function of the cube root, and then we convert it to g of x equals -2 times 3. I'm sorry, -2 times the cube root of x. My bad. So the first thing we see is that we have a negative on the outside. So then we know that's a reflection across the x-axis. And then -2, the absolute value of that is 2. So then I know that that's greater, right? 2 is greater than 1. So it has to be a vertical stretch by 2. Anything that is vertical is straightforward. You can grab the number and it is what it is. Anything that's horizontal, you always have to put a little bit more work into it, right? You either have to take the reciprocal of it or you have to factor something out. Yeah. Okay, the domain and range for both of these, even with this transformation, is still all real numbers, which is -infinity to infinity. And a lot of the time, you can just type it into decimals, right? And then you can see what the domain and range would be. Now, for cube roots, it's a little easier, right? Because it doesn't matter what the transformation is going to be. The domain and range is still going to be the same, negative infinity to infinity. But if you have a square root function, when you apply transformations to that, that will change. There is going to be something that changes there. Okay. All right, so let's go to example 1. So we're going to describe the transformation and then just do a sketch of it. So, see, y'all always get the better version of me, because let me tell you, 6th period was a hot mess. Okay, so we have a graph right there, because I'm going to get ready to sketch that in a minute. Now, this one, f of x equals square root of x, it's the parent function, right? So that's cool because it's the basic one. I only see an x on the inside. There's nothing else I need to mess with. I'm sure that if you look at example 2 already, you can see that there's a difference there already, right? My original has x plus 2 in example 2, but example 1 is easy, so we're good. Don't stress. Okay, so this part y'all are pretty good at, so I'm just going to go on ahead and do it. So that plus 5 right there is inside, right? So I'm going to put in, it's inside my radical, which means it has to be a horizontal transformation, and it's adding 5. So I'm going to think opposite, which means it's going to go left 5. Let me zoom in a little bit here while we're writing that. Okay, so it's going to go left 5. Then on the outside, we have a minus 6. Well, this is outside, so I know it has to be a vertical transformation. Now, oops, my bad. So remember, anything that's vertical is just really straightforward, right? So because it's a minus and I know it has to go down 6. So that's the only thing that's different, comparing it back and forth from f of x to g of x. Those are the only 2 numbers that are different. So that's it. That's your transformation. Now, to graph your new function, really all you have to do is plug numbers in, okay? So, okay, so let's go on ahead and do that real quick. So if I wanted to graph this, I'm going to choose x values, and then I'm going to plug it into g of x, right? So you can choose any numbers. Because I'm dealing with the square root, I'm going to think smarter, not harder. I want to choose numbers that are going to come out pretty, right? You can go in order, right? You can get decimals. It's not that big of a deal. If you look at the example I gave you up here, when I chose my table, I just went in order. I went -2, -1. Hold on, this is the part I'm talking about, right? So when I looked at my x values, I just went in order. I went -2, -1, 0, 1, 2. But you can see that I ended up with decimals, right? So you can do that. That's fine. But I'm going to try to choose maybe a few more prettier numbers that I know will come out better. So looking at this, I'm going to have x plus 5 square root whatever I get, and then subtract 6. I don't care about the -6. I want that inside part to come out a little prettier. So obviously, if I do 0, you're going to see that 0, the square root of 5 is not perfect, right? But what is perfect? Well, 4. Well, how can I get 4 out of that? Well, if I let x be -1, right? Negative, so then we would have, let me just show y'all. Let me show y'all that work that goes into that. -1 plus 5, right? Then outside, -6. So -1 plus 5 is 4. The square root of 4 is 2. 2 minus 6 is -4. So my first ordered pair would be at -1, which is right here. And then -4, let's make that there. Let's make this -6. Now, if you remember, hold on. Okay. So if you look up here, right, in a quadratic formula, we know that my HK is always my vertex, right? It's an important point on my function. This does not change. This HK is still important. I just don't know what it's called. I tried to figure it out real quick. I don't know what it's called. I'm sorry. I'll go look it up and see if it has a name, but I don't know it. It really doesn't matter. Okay, no one's ever gonna go up to you and be like, "Hey, do you know what that point is called on a radical function?" No. Okay, it doesn't matter. All right, cool. So that HK is important though, right? So this right here, we already know that's really a -5, and this would be a -6. So you can actually plug that point in. So -5, so here's -1, -2, -3, -4, -5, and then -6 would be about here. So this is actually where your root function is going to start. You can connect it and it should look something like that. And then I'll even show you on our table. So if I let my x, right, here's x, y. If I let my x be -5 and I plug that in, I would end up with -5 plus 5 minus 6. Well, -5 plus 5 is 0. The square root of 0 is 0. Subtract 6, it's -6. So you can see that -5 and -6 was your HK. Okay, so I didn't just lie. That came from somewhere. Anyway, so let me go on ahead and graph my parent function so y'all can see the difference. So this right here would have been my parent function, right? Now, our transformation was left 5 and down 6. If you look at the original, which is the blue one that I just drew, this is f of x, and then this one's g of x. If we count, you're going to see that from this point in the origin to this HK that we drew over here, right? This was our HK, -5, -6. You're going to see that it's going to go 1, 2, 3, 4, 5, 5 left, and then 1, 2, 3, 4, 5, 6, 6 down, which is exactly what our transformation was. Anyway, I just wanted to point that out. Okay. Now, example 2. We have x plus 2 is our original. Now here, you're going to notice, so I kind of want y'all to still be able to see 1. You should notice that for f of x, this time we have a plus 2 inside. So we're not looking at the parent function. We're looking at a transformed version of the parent function already, but that's fine. It doesn't really matter. You should still be able to tell me how it changed by comparing them. You could also just graph it in decimals, right? And look at it visually. I like graphing stuff on decimals also. Now, the first thing we should notice is that we have a negative right here, right? So a negative means it's going to be a reflection across x-axis. And again, that was on the first page of your notes, so you should be able to see that. Then we would do the absolute value of of whatever you're multiplying in the front, which is really just 1/2. 1/2 is between 0 and 1. And also notice that it is outside, right? That 1/2 is outside. So you should be able to tell me, is that going to be a vertical transformation or horizontal? If it's outside, we know it has to be a vertical, and 1/2 means that it should be getting wider. So if I have my hands vertically, what's going to make it get wider? Is it going to be when I push into it or I stretch out? So when I push into it, if I were to hold a ball right here, you could see that it would be squeezing out, right? So it's going to be a vertical compression. And if I scroll up to the top, where I gave this to you at the top right here, you can see that a vertical compression, which is what I just wrote, is when your number is between 0 and 1. So that's at the top given to you, but I was able to identify it just from knowing what it should be. Okay, now let's do this part. Obviously, we have a +6. In my original, I don't have anything there, right? So it's just a +0. So I can just say, oh, well, I know what this does. This is going to go up 6, right? That's the easy part. I left the trickier part for the end. Here, we can see that we already have a +2. We already said that. But then in my new one, I have a -3. Okay, so when I have that, if it's a translation inside versus outside, I like to draw number lines. okay? So I know, remember, anything that's inside is always opposite. So this is -2, and this really is a +3, right? So then I'm going to draw a number line with these two numbers. So I have -2 and +3. So to get from -2 to 3, I'm going to go right. So I know my transformation is going to go to the right. Now I need to know how many. So -2, -1, 0, 1, 2, and then there's 3. So 1, 2, 3, 4, 5. So 5 units to the right. So my transformation here is actually 5 units to the right, not the 3 that you would assume. Okay, so let me do like a mini rough sketch of that. Okay, so my original started at -2, so here's -2, right? So my original looks almost like my parent function, but it's just starting 2 units to the left. Now, for my new one, you can literally just kind of like look at this and kind of figure out where you're supposed to be at, right? So you're going to go right 5. So that's 2, so 3, and then up 6, which would be about, let's make it about here. Oh, and then a reflection across the x-axis, which means this should, instead of going up, it's going to have to go this way. Oh, but then it was a horizontal and it was a vertical compression, which means it's pressing down. So it has to lay flatter a little more than that. Now, obviously, I just kind of looked at the transformations that I identified, right? To graph it, I started with the point, I moved it how many ever units, and then I looked at my reflection, and then if it was a vertical compression or whatever, you could just do what we did with the other example and make yourself a point, right? I mean, not a point, I'm sorry, a table. So if I do X, you can do 0. Wait, what number would I want to start at? 3. You obviously can't do 0 because that would not be part of it, right? So we would want to start at 3. Yeah. And then you would plug it in. So 3 minus 3. So 3 minus 3 is 0. So you would have the square root of 0, which is just 0. So -1/2 times 0 is 0. Then plus 6 is 6. So when X is 3, your Y would be 6, which is exactly what we have here. Right? That's where we started at 3, 6, which is our HK. We talked about that. That right there is your HK. It's just called the starting point?
Mm-hmm.
Oh.
Because it moves.
Yeah.
So they can't say Y and insert, they can't say
yeah,
X
no,
and
it's
insert. Yep. So
oh.
that's how they started.
Okay, so thank you, Mr. Brown. We just figured out what that dot, it's called the HK. It's just called your starting point. Well, who would have thought it would have been that easy? I'm sorry. Vertex for quadratics and, vertex for absolute value. And anyway, well, it's called your starting point. So your HK is called your starting point. Okay, there you go. Anyway, so if you keep going, right? So then obviously it's going to go this way. So what would be another? So 12. 12 minus 3 is 9. The square root of 9 is 3. So we're doing 12 right now. So then 3 times -1/2 would be -1.5. -1.5 plus 6. Ay, Dios mío. That would be 4.5. So when 12 would be like way out here, right? That would be like 12. And then 4.5 is right about here, which actually looks like it would fall into like that little rough sketch that I just did. Bam. Anyway, sorry for doing that in my head, but you'll be all right. Okay. Example 3, let G be a reflection across the x-axis followed by a translation 2 units down and 6 units left of the graph of f of x equals 5 times the square root of x plus 3. Okay, These look way harder than what they are. They're really not that hard. You just plug it in and simplify. Okay, so let G be a reflection across the x-axis. So I already know what that looks like. That means I'm going to have a negative out here in the front. So that's step number 1. Then translation 2 units down. So if I'm going to go 2 units down, that means I have to have a minus 2, bam. And then we have 6 units left. Well, 6 units left means it needs to be on the inside. We already have a +3. I don't care. You're still going to write what you need to write. It's 6 units left, so that means I'm going to put a +6, right? Okay, so then just put a +6. That's going to go on the inside with that one. So what we really have right now is g of x equals -5 times the square root of x plus 3 plus 6, and then a -2. So to get your final one, just simplify it. Well, what's 3 plus 6? 9. There you go. That's your new equation. So it's really not that hard the way you think it would be. Like if there's something already there, okay, whoop-de-doo. Just plug it in and then you're just going to simplify it anyway. And then there's your new rule. So for example 4, same thing. We have a vertical compression of 1/2. And remember, anything that's vertical is straightforward. So you don't have to do the reciprocal of anything. You don't have to do the opposite of anything. The number they give you is the number it is, and then that's it. So I know I'm going to have to, because it says vertical, this means outside. So I'm going to have to multiply 1/2 to the outside. So I know I'm going to have a 1/2 out here. I'm just kind of plugging it in there. Then I see a translation 2 units up. Up, well, we know up is vertical. So I know that's also going to go on the outside, and it's vertical. And because it's up, I know it has to be a +2. Well, you're going to notice that you already have a -7. I don't care. I'm going to put my +2 right after it. And that was it. So then now all we have to do is simplify. The only thing here to simplify is that right there, -7 plus 2, which is going to give you a -5. So we're going to have g of x is equal to 1/2 times the square root of x plus 4 minus 5. You're done. That would be your new rule. Now, where it would get a little messy is if I would have asked for a horizontal compression instead. If I would have asked for a horizontal compression with a translation 2 units up, that would have been a little different, okay? So just so that y'all can kind of like see what that would look like. You're not going to do that in here as much. You really do that more in pre-cal, but it's good to get exposed to it. So let's say instead I ask for a horizontal compress of 1/2. I'm not going to change the number, right? So if it said a horizontal compression, anything that's horizontal, you have to put a little bit more work into it. So that 1/2, you can't just plug it in. You would actually have to find the reciprocal of it, which would be 2/1. So the number you would be plugging in is 2. So instead of a 1/2, you would be plugging in a 2. So you would have g of x equals the square root. And remember, horizontal is inside, 2 times whatever you already have, which is x plus 4. So you can't just put the 2 in there and then be done. Like, no, you have to multiply everything inside of the radical or your parentheses or whatever you're looking at by the number that you're compressing or stretching horizontally. Then obviously the -7 and the +2, because it's outside, you would just be able to leave that alone, right? So it would be -5 minus 5. So then you would just simplify. So 2 times x would be 2x on the inside, and then 2 times 4 would be a +8. So your rule, if I would have asked for a horizontal compression, would have actually looked like this. If I asked for a horizontal compression instead of a vertical one. Just so that y'all can get that in your brain a little bit, okay? I'll try to throw them in a little bit more often so y'all can get used to it from now until pre-cal. Okay, moving on. Okay, so here's the fun stuff. And not even yet, because we're really just doing basics today, okay? Anyway, so for tomorrow's notes, did I already put them on here? Tomorrow's notes look like this, right? And remember, I was talking about it a little bit, right? So tomorrow we're going to be reviewing our laws of exponents a little bit more, okay? But two of the laws that we needed for today was the ones I just put. Where are they? Oh, wait, wrong period. Sorry. Okay, these, which is rational power and negative power. Okay, so the first thing we need to know, remember, rational means fractions. Radical means the little root symbol, okay? So you can see that here we have an exponent that's a rational, which really just means it's a fraction. That's all that means, okay? Rational means fraction, okay? So we have an exponent that's a fraction. This law, it tells you what you do with that fraction as an exponent, which basically means you can convert it into a radical, okay? Now, you're gonna notice that right here, I put bottoms out because that's how I remember how to write it, which, I mean, really, your denominator, do y'all see that N? Whatever's at the bottom goes out, that's it. So that's how I remember what my radical needs to look like, right? Because you have a top and a bottom, you have a numerator and a denominator. So if you look at example 1, right, we have 16 to the power of 3 over 2, right? So whatever's at the bottom in that exponent as the fraction, that's what's going to be your root symbol. So because we have a 2 there, this is going to go out. So we're going to have the square root of 16 cubed. Ta-da, you're done. That's us applying the law. That's it. Now, the other law we're going to be using that you should have done in Algebra 1 is negative power law, right? So a to the power of negative m, which basically means if you look at the law, all we're doing is that if I see a negative exponent, you can see that it magically kind of like goes away. Well, the reason that happened is because we slide to the other side. And notice I didn't say you move to the bottom. I didn't say whatever. I put slide to the other side because if you have a negative on the denominator, then you grab that entire base with its power and then you're going to move it to the other side. So it doesn't matter if I give you a negative exponent on the top or the bottom, wherever it's at, you're going to throw it to its opposite side. Okay. So, real quick before moving on, I do want to talk about simplifying radicals because it's probably been a good minute since you've seen it. So just to expand on this, right? This is obviously converted to a radical already. Now, if I wanted to simplify this further, I can. So a square root, okay, so before we do that, let's talk about what square roots are, right? So if I take the square root of 16, what is the square root of 16?
4.
And why is that?
4 times 4 is 16.
So how many 4s did you multiply? 2, right? So we know that 4 times 4 is 16. So all I did, do y'all see how I'm just breaking it down? So the square root of 16 is really just 4. Now, right here, do y'all see how in this little nook, right here, do y'all see how there's no number there? There's a number there. It's really a 2, right? So if I write the cube root of something, you know that that's a cube root because you see a little 3 there. Square root is the only one that you don't have a number, right? So if you don't see a number in there, it's implied a square root. You've been doing that since you were, I don't know how old, okay? Now, the reason this works is because you have, the way I like to think of it is that you have essentially a group of 2 of the same number, right? 4 times 4 is 16. So I'm able to take this 4 out because this root symbol is telling me to take out groups of 2. The number inside that group is 4, which is what we got here, right? So let's do so if I gave you the cube root, let's do an easy one, of 8. Well, what would the cube root of 8 be? Well, what it's really asking for is what number can I multiply 3 times to get this one, right? So we would have the cube root of, well, 8 is really 2 times 2 times 2, right? 2 times 2 is 4, 4 times 2 is 8. That's where that comes from. So you have one group of 3. So do we see how that works out, right? So if I ask for the fourth root of something, so what's the perfect fourth root? 16, right? Why? How does that work? Well, the fourth root of 16, so that's 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. Bring down the last times 2, that's 16, right? What does that mean? I have 4 2s that gives me that 16, okay? So this little number right here in your little nook is pretty much telling you, hey, I want whatever number, I don't care what number it is, but it has to be in groups of 3, or it has to be in groups of 4, groups of 2, okay? So when you're looking at this one over here, going back to example 1, this is a square root of 16 cubed. Yes, I could do 16 times 16 times 16, but I already see the power of 3, so I'm just gonna simplify it by writing the square root of 16 times 16 times 16. This is a square root. So how many groups do I want? Groups of how many? What's a square root? If it said cubed root, it would be 3. But if it's a square root, it would be how many? 2. So do y'all see how I have 2 16s right there? That means that I can just take that number out one time. So then what do we have left? Well, we're left with the square root of 16. Well, what is 16 made out of? Is 16 a perfect square? 4 times 4. So we have that one group of 4, and we're gonna take that out. So out here, we have 16 times 4, and there's nothing left, right? Well, 16 times 4 is 64. Okay, that's just me getting y'all used to the simplifying and stuff, okay? The rest of these, we're not gonna spend that much time on it. Maybe 1 or 2 we will, but the rest of them, we're just gonna do the easy stuff and like convert it to radicals. So for example 2, we have 18 to the power of 1 over 3. What's gonna go on the outside? Type it in the chat. So in the chat, what's gonna go on the outside? So 18 to the power of 1 over 3. What number is gonna go on the outside? Because that's gonna be the root I'm looking for. Yeah. All right. So whatever's at the bottom is going to go out, right? So then this is the cube root of 18. Oh, I forgot to give you my little analogy of the cowboy. Okay. So you know how the bottom goes on the outside, right? So it's kind of like a cowboy who's riding his horsey. Like that. Okay. Now, once the cowboy and the horse arrive to their destination, does the horse go inside the house with the human? No, it does not. No. Okay. So the cowboy goes inside the house, right? So this is your cowboy right here. Yeehaw, right? And then your horse is at the bottom because you're riding the horse. See, and your horsey stays out there waiting for you, and then the cowboy is inside. Anyway, okay. All right. So cube root of 18. So usually when I simplify these, I just like to break it down into factor trees. which is why I gave you a list of prime numbers, because those are the numbers that I'm always looking to pull out, right? So 2 times 18, 2 times 9 is 18, and then 9 is 3 and 3. So you can see here that your 18 is, its prime factorization is 2, 3, and 3. Do I have a group of 3 that I can take out? Remember, they all have to be the same, right? I have a 2, a 3, and a 3. Do y'all see how I can't take anything out, right? So then that means that this is my simplest form. Oops. Now, for example 3, what do we notice that's different with the exponent from -1 and example 1 and example 2? What do we notice is different? What do we have there? I'm gonna get a drink while y'all figure that out. Ooh. I got this. I think I put my fridge so close to me. That's right. Okay. You guys, y'all are missing it. No, I circled it already for you. The negative. Do y'all see that negative in the exponent? Y'all really don't see the negative right there? Right there. Hold on, right there. Oh, I can't, right there. Do y'all see that? Do y'all see that negative in the exponent now? Matt, you lying. Okay. So when we see a negative in the exponent, we slide to the other side. So this is going to be 1 over 81 to the power of 3 over 4. Now we can set a radical in the denominator. So we would have 81 to the power of 3, and we want the 4th root of that because the 4 would go on the outside because it's at the bottom, so bottom's out. Oh, that's bubbly. Okay. Now, we could simplify that. I have the room. Why not? So if I have 1 over the 4th root of 81 to the power of 3, well, what does that mean? Oh, no, wait. Oh, this is the one I didn't want to do. Never mind. Just kidding. I realized it with 6th period. Never mind. That's my final answer. We're going to leave it at that. Okay, cool. Moving on. So now we're going to write each expression using rational exponent. So now I'm giving you a problem in radical form, and you're going to go in reverse, right? So if you know that the horse is outside waiting for you, when you leave the house, where's the horse going to go? Where's the horse going to go, you guys? Where's the horse going to go? Yeah, do you see how different 6th period is compared to 7th? They're like polar opposites, right? I know. Not saying that it's a bad thing or anything. It's not. Y'all are just way different. Oh my God. I don't know what I'd rather have. I can't say anything because what if they watch this video later on? I love y'all 6th period. I love y'all too, 7. Okay. Mr. Brown, where would the horse go if you leave the house? Where's the horse going to go? You got to get on the horse. You're right. You got to get on the horse. So this horse got to go to the bottom. So we're going to have 16 to the power of 2 over 9. And we're going to leave it like that. So example 5, it's because I was going to simplify some of these, but nah. So for example 5, what do we have? Let's look at the law again, right? We have, so we're starting from here now, right? And whatever's outside is going to go to the bottom. So we have this 4. Oops, my bad. There it goes. So this is going to go to the bottom. Now, inside my radical, you should notice that we have 29 times y. And this entire thing is underneath the radical. So we're going to have 29y, the entire thing, to the power of 3 over 4. Here, let me write this bigger. I'm over here writing small and I have all this room. I am not thinking. Okay, example 6. Now this, you could take it all the way back to the beginning, right? So first of all, again, we can see we have parentheses. Now, we have the root symbol, but no number there. So what root do we have? What's the number there then? 2, thank you. So that means this 2 is going to go back at the bottom, right? It's the horsey. So whoever's inside the house, they're going to jump back on the horse and then they're going to go riding. Oh, wasn't there like a riddle? Like some guy rode into town on Saturday, left 3 days later left 3 days later and it's Friday. How is this possible? Yeah, it was something. Have y'all heard that riddle before? Yeah? Okay. I don't know. You think about it. So we have 1 over, remember, the whole thing is inside the radical, so it's 3k to the power of 5 over 2. Now, you could rewrite this, right, if you didn't want it in a fraction. Because this is at the bottom, then I know that I can give it a negative exponent. You don't have to, right? So another optional answer would have been 3k to the power of negative 5 over 2. But this would have been fine enough for me. I don't know. Okay, so this last one on this section. So example 7, we have cube root of y to the power of 6. Remember, if we're going to go in reverse, whatever the root is going to go back under, right? So then we would have y to the power of 6 over 3. Oh, well, look at that. What's 6 divided by 3? 2. So this would simplify to y squared.
He took 2 different horses.
You're kind of going towards the right track. But no. Now, with example 7, I did want to talk about how you could use, I guess, a factor tree to simplify and get the same answer, right? So we know that this is a cube root of y to the power of 6. Well, that 6 means I have 6 y's, right? 1, 2, 3, 4, 5, 6. What did we talk about earlier? We talked about that, how that cube root, that means I want groups of 3. Well, how many groups of 3 of y's can I form? 1, 2. That means I'm going to take 1 y out and another y out. So what's y times y? Y squared, which is the exact same thing I get there, but 2 different ways. Write each expression in radical form. Okay, so we kind of get the gist of this, right? This would be bottoms out. So this would be the square root of 7x, but make sure we understand that it's to the power of 3. Or we could also write it as 7x to the power of 3. Both of these are the same thing, right? So you could have put the parentheses inside the radical, or you could have just put the parentheses outside and with the power of 3 on the outside. Now, I could simplify this, right? So this is one I should have written smaller in. So we have inside our square root, we have 7x times 7x times 7x. Well, you would notice that you have 2 groups of 7x's. So you can take one of these out. So this would equal 7x times the square root of 7x. Sorry. We see a negative here. So we're going to throw it to the other side. So 27b to the power of 4 over 3. And we're just going to have a 1 on top. And we'll talk about why or where that 1 comes from if you don't understand why that 1's there next time I see you, which will be Monday. Now, keep converting this or not. Yeah, whatever. So then we would have 1 over, right? Bottom out. So we're going to have the cube root of 27b to the power of 4. And that one could also be simplified. Okay, I'm gonna give y'all like 15 seconds. Go do C. So just write it in radical form. Brian, you done? Write it in radical form. Okay, so which number is going to go on the outside, the 3 or the 4? Brian, thank you. 4. So we would have the 4th root of all of this, 10y to the power of 4 to the power of 3. Now, if you wanted to simplify this, we could. Let's go ahead and do it. Why not? So that means we would want the 4th root. We have 3 of these, right? Because it'll help with tomorrow. 10y to the power of 4, 10y to the power of 4, 10y to the power of 4. What we see, so let's go ahead and rearrange this because it'll help us see it a little bit more clearly. I'm going to put my 10 times 10 times 10 together because I have 3 of them. 1, 2, 3. And I'm going to put y to the power of 4, y to the power of 4, and then my y to the power of 4. I want groups of 4, right? So these 10s aren't going to go anywhere because there's only 3 of them. So I don't have enough to take out. But these y's to the powers of 4s, we already have 4 right there. So I can take 1 y out. We have another y power of 4. That's another group of 4, right? So we can take another y out. And then we have another group of 4 right there. So we can take another y out. So we have 3 y's out here. So that's going to be y to the power of 3, the 4th root of whatever 10 to the power of 3 is. I don't feel like figuring that out. So simplified, that would be your answer. Well, 10 times 10 is 100. 100 times 10 is 1,000. So 1,000 would be on the inside. Wait, you can't see what? Oh. Did it make it bigger? I did something right now. Did it do anything? Or no? No? If you go to the top where it says view options and go to zoom ratio and click like 150%, it'll zoom in bigger for you. And then you can just move it around. Let me know if that helps. Did that help? Okay. And then for the last one, again, we see a negative. So because you see parentheses, that entire thing is going to have to get turned into a fraction. So we're going to have 6x to the power of 5 over 2. And now we can convert that into a radical. So 1 over the square root of 6x to the power of 5. Could I simplify that? Yeah, you could. But we're going to leave it like that. Okay, so this practice part down here, I really just put that because I accidentally skipped a page. But it's good practice for what we're about to do, which is learn how to simplify radicals, okay? So we're gonna do the first one and the second one together so y'all can get that going, okay? Because you have to get good at this. It's not enough, like you need to get better. So we're gonna start with basics, which to me, in my opinion, is factor trees, okay? So when I do factor trees, I just try to factor out prime numbers, okay? So 294, what gives me 294? 2 times, because 2 is a prime number, so 294 divided by 2 is 147. 147 is not divisible by 2, but it could be divisible by 3, which it is. 147 is 3 times 49. And then we see that 49, well, it's 7 times 7. So that means that this is my prime factorization, right? 2 times 3 times 7 times 7 will give me 294. Now look at the root symbol. My root is square root. So what does that mean? I want groups of how many? I'll wait. Like, answer in the chat. So square root means I want groups of how many? There you go. Thanks. Okay, better. So I want groups of 2. So do I have any? Good. So we can see we have that one group. So that means that I can take out 1, 7. So we now have 7 times the square root of whatever got left over, which is 2 times 3. Well, what's 2 times 3? That's 6. So my simplified answer would be 7 times the square root of 6. So for number 2, this is an easy variable example. So we know that this is x times x times x times x, right? And square root means I want groups of 2. So 1, 2. That means that I can take out one group of x and then another group of x. So on the outside, I end up with x squared. And then that's it. That's your answer. There is nothing left inside the radical, so your answer would be x squared. Now, someone last period was like, oh, you could have just converted it back to a rational exponent and simplified. So, right, this could have been x to the power of 4 over 2, which is just 2, which is also x squared, which is the exact same thing we got here. Okay, so all of these are pretty much the same thing. some numbers, some with variables. There's only 4 more problems on that. Okay, so your assignments have been posted on Canvas. Just, you can give these a try, see how it goes. You can ask me for help later. But for your assignment, you can use Desmos. Oh, I forgot to talk about domain and range. No, yes, I did. I did talk about domain and range. Oh, no, I didn't. Okay, so go back to example 2 real quick because you're going to need it for your homework. So for example 2, remember your domain and range, you're just telling me where you're starting and where you're going, right? So if you look at, let's do example 1 because I have a little bit more room here. For my domain, this is what I wanted, right? Where is it starting? It's starting at -5 and it's including that. So -5 to positive infinity. Ta-da, there you go, right? Because of the arrow, so it's going to infinity. Then for my range, remember your range is up and down. So it's starting at the bottom right here at -6. So that means it would be -6, 2, and it's going up. So that would be positive infinity. For example 2, same thing, but remember we were looking at this one, right? This was f of x, the original. I want the domain and range of g of x. So my domain for g of x would be, well, where does it start? It starts on the left side at this number right here, which was your h, which is a +3. So it's including the 3, and then it's going to the right to positive infinity. And then my range, same thing, but here we can see that it's going down to negative infinity. So it's going from negative infinity all the way up until this 6 right here. Ta-da! There you go. There's your domain and range. So remember, when you're writing an interval notation, the reason I put that negative infinity is because you always go from least to greatest, okay? So if your smaller number will always go first. So because it was upside down, and yes, it's starting at 6, right? And it's going down from there. You don't want to write it like that. You want to write it properly. So I put my negative infinity, and then it's going to go to 6. That's really just it there. Okay.